Hello everybody and welcome back to the M86 mainframe channel. This is M86 and today we're going to be having some fun with PL1. As you know, PL1 is one of my all-time favorite programming languages. The other ones I guess would be C and Golang and of course I have always had a weakness for or fondness for assembler, especially on the mainframe. But if you see a trend there, PL1 and Golang and C are actually all in the same family, because what happened is that PL1 itself is a descendant of Algol, Algol being the mother of all this procedural languages of this family. So Algol then influenced in the 60s the standard PL1, and which was pushed by IBM. IBM with PL1 wanted to create a language which would be as good to use in a business environment as COBOL, and as good to use as Fortran in a scientific environment. And they produced a language which I think can do both, but it never really became the one language that replaced both COBOL and Fortran. I did use PL1 in the 80s for business kind of applications. I was in the military then, but those were not scientific applications. There were other applications, and it can absolutely be used for that. And then from PL1, a language called BCPL was made out of that on the Multics environment, because Multics itself was written in PL1. And from BCPL they then wrote B, the predecessor of C, and then they wrote C, of course, and then from C we have a very direct lineage to Golang, the Go programming language created by Google. So I like it a lot. I do a lot of stuff in PL1, and today we're going to be playing with that. And the reason for this new PL1 video is that I've had for a number of years a PL1 compiler for Linux, and everybody can go obtain one by going to Iron Spring. If you search for PL1 and Iron Spring, you will end up on this website, and you can download from there Windows, I think, and the Linux version of this PL1 compiler. It is an optimizing compiler, but it is, of course, I want to say a primitive compiler, but it does its job. And what I really like about it is that it compiles PL1 compiler from the MVT-F compiler we have on MBS 3.8 TK4 without any changes. You can just import the source code and it will compile it. And so today we're going to be looking at first how the two compilers manage, how they compile stuff, and then we will, since we are able to take change source code from the mainframe and run it on the Linux machine, we can actually benchmark what is the impact of the Hercules emulation on to emulate the mainframe, because we're going to take the exact same program and run it once on the mainframe and run once on the underlying same machine Linux. So it's actually a laptop with an i5 processor, and we're going to run the PL1 compile and then run the PL1 code. And we'll also on the same machine have an MBS instance running and run the same code inside MBS on Hercules on that same machine. And this will give us a feeling for the overhead of emulating the mainframe, but also, of course, this will give us an understanding of how good the compilers are, especially once we turn off all optimization. So let's go and have some fun with that. I already downloaded this. In fact, I've had it for a number of years on my laptop, and let's see what we're going to be playing with. Whenever I have to learn a new programming language, or whenever I need to play with a compiler, the first thing I do is always write a solver for the n-queen problem. And the n-queen problem is you have a chessboard of n times n two-dimensional fields, and then you need to place n, that's as many as fields as you have, the same amount of n on the chessboard of queens, so that no queen can threaten the others, and find out all the permutations of these positions of queens that you can place on such a board. So the standard, of course, would be an 8x8 chessboard with 8 queens, but I go much higher. I go to 13, 14. I've calculated up to 16. I think the world record is 25. There's probably at least two ways to solve this problem. One is using recursion, which is well understood, and then the other one is using backtracking. I don't like to use recursion when I horse around with compilers, because when you do recursion, you're really just testing the efficiency of the operating system and allocating and destructing stacks for the recursion functions. And so therefore a lot of overhead goes into allocating stacks, and it's not really something that has to do a lot with the compiler, even though of course some compilers do their own stack management. But when you use backtracking, you avoid all of that, and it's all running within the algorithm. And so what backtracking is a way to, first you place a queen, and then you advance it, and then you place another one, and you move them up, and the moment one is threatening the other, you actually go back one step, and so that's called backtracking. There's a lot of material that's really just computer science, nothing to do with this M86 mainframe channel, but backtracking algorithm. I'm sure there's also a YouTube video for that. Yeah, in fact, they even have one for the n-queen problem. So there is one specifically for the n-queen problem with the backtracking explained. So I'll actually link to this video in the description below this video, so you can see how this algorithm works, because I think that's exactly it. The only thing is that I don't actually need a two-dimensional board representation. I can get around it. I wonder if you can find out how I get around it by looking at the code. I'm going to be linking to the code that is on my GitHub repository in the description below this video. It's going to be here. GitHub M86. Let's see what it finds. And we should have here, yeah, here is the well, I have one implementation in Go, but it's exactly the same as this one in PL1. So see if you can find out how I avoid having two-dimensional chess representation. I will be linking to this and to the other one. It should be here somewhere. Repositories, queens. It's probably here. Yeah, in the MBS repository. And queens. Yeah. So this exact PL1 program is in the repository, unchanged, and you can study it. And this is what we're going to be playing with today. So here's my code. I just took it down with a terminal download from MVS, and let's log in here and look at the same code. Yeah, let's make this a little bit bigger. As you can see here, other than the JCL part, which of course needs to be there, we're going to be doing its exact same code, unchanged. I just downloaded and removed the JCL part from the beginning, this part, and then put it in here. So this is the code. Now I have this PL1 compiler here installed, the one from Iron Spring. And let's compile it just so you see I'm compiling it. I use make, so since I haven't changed anything, it wouldn't. Let's put in here a comment. So there's two external variables which are kind of global variables. Okay, I'm just putting this comment here to force it to recompile, because I use make as my building structure. So I have two variables. Oops. As you can see here, one is A35. I mean, 13 or 14 would be enough. I just use up to 35 to be on the safe side. I think supercomputers have solved up to 26 or 25. That's the most people have ever solved. And then I have a counter, a global counter, so that we can count how many solutions we found. And then I have here some. If it's below 4, there's no solution, so I discard it. If it's more than 35, would take weeks as a year, or a supercomputer, but we can also just say more than 20. Of course, I use here Vim, the world's best compiler, and I know I'm going to have some comments in the in this video because a lot of people disagree with my choice of editors. I just love Vim. It's an amazing editor. I think it's just the best editor out there, and I know a lot of other people disagree with me, and you're welcome to post your disagreement and anger in the comments below this video. So then once I do some sanity check, I call the procedure that places the queens, well, that checks the positions, and that in turn places the queens here in this function. Important here to note how the counting is done. We then take the absolute value, so we can eliminate, so that we don't have to. I'm checking for diagonal positioning here, and then we calculate, and that's about it. So very simple code. There's nothing special there. Let's just say make and queens. Okay. So now what we're going to do is we're going to run this with 13, as you saw here. We run this for a chessboard of N13, so 13 by 13 fields with 13 queens. And let's note how long this will take. So time and queens. So we let Linux do the timekeeping for us. Okay, so this took 5 seconds, 5.6 seconds to calculate 13 with the N13, and there's 73,000 solutions. Now let's write this down somewhere. Mushik's results, and let's just copy this. Okay, so Linux on i5. Let's put this here. Okay, and so now we're going to run this on the same computer, and I can show you that this is the same. First of all, let me save this. Because you will see that I have somewhere here Hercules running. Where is it? Yeah, so you can see here this is running TK4. It's on the same system, and in fact if I switch window, you'll see here the moment I launch this that this is gonna the MIPS counter is gonna go up. Obviously this is not multi-threaded, this is just one single thread. Inside a PL1 compiled address space there's actually more than one thread running, but this is detail doesn't really belong to this discussion, but there is more than one thread running, one for the abend and one for the on condition, to catch those on conditions you can program in PL1. That's how they implement it. So there's more than one thread running inside the address space, but the solver itself runs with only one thread. So why don't we launch it, and then we can look at the time it took to execute. So we launch it with we said with 13, just to make sure. Yeah, let's go. And you should see now, yeah, so this is now running at a much higher MIPS, 127 MIPS. Let's go see here if HW is able to see it now. Yeah, so now it picked it up nicely. We're running at 100% CPU, obviously. And let's observe it from here, so we see when we're done. I don't want to disturb the system more than I need to right now, so that it can have the most performance, more CPU allocated to running Hercules. Now what you'll see is I'm running this with optimization turned off, and then we'll run it again with optimization turned on, and then we get two different messages. One message is how good is the optimizer in the PL1F compiler, for which comes back, which is actually a 50-year-old compiler from the 60s, from 65, so it's 53 years old. How good is that optimizer? And also when we run it with optimization on, we can compare it with the optimized version of the PL1 compiler for Linux and see what is the overhead for emulating the mainframe. And what we cannot see, but there's also a hidden message somewhere there, is how good is the optimizer for Linux for the PL1 compiler on Linux. The two are, one is going to be slightly better. I assume that probably the PL1F compiler has better optimization. They had, I think, at one point, 200 people working in Hurley in the UK on this compiler. So I'm sure they put in a heck of optimization in there, whereas the Iron Spring compiler for Linux was written by one single gentleman with whom I've had some interaction last year. So this is now running. We'll have to wait until it's done, since this is not going to be that much to report on while this is running. We could, of course, do this. Let's watch it from inside MVS by launching Imon, and then we'll see also the job Herc01U running here at 100% CPU. We'll also be able to see it from the console log that this is Herc01 has started, called job 57. And so this is what's running here, job 57, address base ID 00A, so 10. There's really not that. This is going to take a while, so why don't I just stop the video and then we'll look at the output of job 57 as soon as it's done. See you soon. And of course I'm back, and of course the moment I paused the video the job actually finished, so I stopped it for nothing. But let's go back and see what the timing here is. So let's go 3.8. We said job 57. That's the last job that ran. So there's only return code 4, minor compiler warning. So let's see how long this took. So this started at 11:16:25 and ended at 11:19:12. So that's if it was 25 would be 3 minutes minus 13, so that's 2 minutes and 47 seconds. Okay, so let's go write this down. MVT F compiler, 2 minutes and 47 seconds. That's 167 seconds. We said 2 minutes and 47. Yeah. So that's 167. 47 or 167 seconds. And important here, to say that no optimization. Okay, so we ran this without optimization. Now let's run this again. With optimization. Let's put in here 2 and let's see. So optimize 1 means it optimizes for compile time, which we don't really care about because this is blazing fast on a modern i5 processor. And then up to optimizes for execution time. So let's run this again. This will be now job 58, if I'm not mistaken. Yep, job 58. So this was 167 seconds without optimizer, and you can see here an ST status, ST for all jobs. You can do it. Yeah, but we only care about our jobs. So there was actually a thread today in the MVS TK4 mailing list about this ST you need a user mod to enable ST to work properly. So let's see how long this is going to take. It shows us how much CPU time it's been using. Basically 1 CPU second equals to 1 real-time second because it's running at 100%. Let's see here how long this is going to take. And then we can copy this line, and in the meantime, oops. And now for the results. Are we done here? Nope. So in the meantime, looks like it's going to go into 2 minutes as well. Okay, so it's done. Good job. So this started at 11:22:43 and finished, so it's 2 minutes and 2 minutes and 9 seconds. So I just want to make sure I got the numbers right before. Let's look again. So this started at, this was without optimization here, at 25:16. Yeah, so no, this is, it's correct. It's 2 minutes and 47. So this only cut about what 38 seconds. So 38 seconds faster. So it's, this one would be 129 seconds. Okay. So this kind of tells us something. What we can also do is optimize for compile, which is going to be meaningless, just to show you. Put in here, and now it's running. And so this is going to be very similar to the 247. I mean, I can already tell you that. So now let's see what we learned from all this. So now we have this a little structured. So on the same Linux processor, this is an i5. When I just run the PL1 from Iron Spring, which by the way I can't turn off optimization for that one, so it does some slight optimization, but as I said, the PL1 F compiler for sure has better optimization. So I have 5.6 seconds execution time for 13 by 13. On the mainframe we have 167 seconds. So without optimization. With optimization we have 129 seconds, say 130 seconds. So what this means is that the overhead, if we assume that both compilers would have optimized the same, but again mainframe is probably better optimized, then this means that the overhead for the Hercules emulation, for the mainframe emulation, is about 20 times, 25 times slower. So that makes sense. That is that is credible, right? About 25 times slower because of the work involved in emulating a computer architecture which only exists in software, right? And then of course if we eliminate the compiler, then we can also see What this also tells us is how good the PL1F optimization is, because it cuts about 38 seconds from the execution of this job. And there's really not that much to optimize if you look at the code. I mean, I don't know where it optimizes stuff. We could probably look at do we have list on? We can go look at the source, at the assembler. Do we have parm? No, so let's play no deck optimize, and then let's put in list source. This should also produce now. Let's put it with 0.8, just so we don't have to wait that long. Okay. Job 60, it should already be done. Yeah. And now if we look here, we should have the assembler, yes. So by having the list option, it produces either the list or the source option, I'm not sure. I think it's the list. We can also have nest, and then it counts the nesting level here, but I don't need that. But we could now go see where it optimized, and I'm pretty sure it's if it optimized, it's in the queen procedure. So statement 46, from statement 46 on, and in fact it goes from 41 to 52, statement 52. Yeah, so already some optimization here. Statement, where are we? Statement number 41. Yeah, so it clearly rearranged some stuff here. I would have to study this in detail to understand where the optimization is, which I will do, but it's outside the scope of this video. It would take me a while, but I'll print this out and I'll study it, and maybe in one of the future videos I'll report where I found the optimization to take place. But it's rearranged. Clearly it rearranged some stuff, and I'm sure there's potential for optimization in my code. But so the classic answer is with 8 queens you have 92 solutions. By the way, you also have to eliminate the mirrored solutions, because if you mirror a solution on its own, like if it was in front of a mirror, then it's actually the same solution, it just looks different because it's mirrored. And it can be it can mirror, of course, 4 ways, right? Horizontal and vertical mirroring. But I will study this. It's actually a good exercise for me. On one of the next flights, longer flights, I'll take a print out and I'll find out exactly where the optimizer did its job. So, but it was able to optimize 38 seconds, which of course is significant. It's about 25% reduction in execution time. So I just thought it's interesting, since we have Linux, we have a PL1 compiler for Linux, and it is able to run the exact same code without any changes whatsoever. I thought I'll make this comparison, and I don't know how scientific this is, and benchmarks are always fun because people always have opinions about them and disagree, and that's okay. I mean, I want to start a discussion here, and please post the comments below this video what you think. I'll be very interested to see, and I'll read all the comments and try to answer all of them. But this looks like it's about 25 times slower due to the overhead of emulating the S370 architecture, and then we'll also got a good understanding of the compiler optimization quality. Now, if we wrote the same program and we used, instead of backtracking, used recursion, you would see that probably optimization wouldn't have as much impact, because it's the stack creation that will have a lot of impact on the execution time. And by the way, stack operations on the mainframe are probably not as efficient as they were on later architectures. Of course, there is stack, but there's little support for stack on the architecture itself. It's there, but it's kind of weird, and so I think that recursion is not natural to the mainframe, and I'm sure a lot of people disagree with me. But and of course on Linux on the mainframe it's done all the time, so it obviously runs. But recursion and stack processing was not at the forefront of the designers of the S360 and the S370 architecture when they designed it. Of course, Amdahl later on did create other companies like CDC that were very good stack computers. Burroughs, of course, is the prime example of a company that produced computers that were built for stack processing with very good algo implementations. Anyway, so that's all. Just if the takeaway from this is this, I'll post these results in the description below this video so that we have something to look at, and your comments are welcome. If you haven't subscribed to the M86 Mainframe channel yet, I would urge you to subscribe now. If you like this particular video, please press on the thumbs up button. Thank you very much, and goodbye.